Good morning. This is the last video, Computer Science 311. This is video 3. Again, we're talking about linked lists. I think this will be a fairly short video. There are a few features that we would like to add to our linked list, and let us just remember our linked list, we had this variable called head, and it pointed to these nodes. And nodes kind of look like this. There would be a string in there that would have a name in it. There would be an age. And it would point to another node. So maybe here's a very small linked list. And the methods that we had defined for this linked list so far, just a couple of them. We had a constructor, okay, that made the linked list. We also had insert front, so that anytime we wanted to add a new element to the list, it always got inserted right up here in the front. Okay, and then we had something, I think we called it print it, that would print out the entire linked list. We want to add a few more methods here. We would like to add, we had insert front, we want to have delete front. Which basically would remove the first element of the list and update the reference head to now point to the next element in the list. We would like a method called find. For example, I might want to find Mary, and it would go through the list, and when it found Mary, it would print out this entire node over here. Okay, maybe a simple one called list length, that would just come back and it would say to us, oh, this list over here has a length of 2. These are all pretty simple. These two are actually going to be fairly similar here in that find, of course, is going to start over here and it's going to go through the list until it finds the particular key, the key being the name that we're looking for. I'd come over here and I'd go, well, is this Mary? And it would go, no. So I'd come over here and I'd go, is this Mary? And it would go, yes. And we would stop. If I were looking for Stan, is this Stan? No. I'd come over here. Is this Stan? No. I'd come over here. I'm off the end of the list. So I would indicate that it was not found. So that's fine, which is very similar to list length. List length is just going to go through here, and each time we look at a node, we're going to increment the counter by 1. So these are very, very similar in that they almost look like linear search. Okay, so for example, if I were to come along here and I were to say public int, and I'm going to call it list length. I would come over here and I would say count is equal to 0, int count. And then I would come over here and I would have node rover is equal to the head of the list, and then I would just have a loop here that would look like the following: while rover doesn't equal null, what do I want to do? I want rover to equal rover.getNext, and then I just want to increment my counter. And I would finish this up by returning count. And that's it right there. So I have to ask a couple of questions about this. Suppose the list is empty. In other words, suppose I had a situation where head looked like that. Well, notice I initialize count to 0, and if rover is equal to head, then rover is going to have the value null, and this is immediately false, so it would skip out of the loop here, and it would return 0. So that appears to work. Suppose I had a situation like this. Here's Bill, 23, and it looks like that. Initially, count would be 0. Here's head. Rover would be equal to head, so rover's pointing at Bill. Rover's not equal to null, so it would say rover is equal to rover.getNext. So it's now equal to null. But count got incremented. Count is 1. I'd come up here. This would now be false, and it would return 1. You'll all excuse me while I let my cat out of the room. Okay, Kitty is outside now. So I'm pretty certain that this is correct. And I'm going to come over here, and I'm going to add it to here. So I'm going to say, I need to move my tablet. Public int, and what did I call it here? I called it list length. And I'll come over here. Whoops. And I will do the following. I will come over here and I'll say int count equals 0. And I'll come over here and I'll say node rover equals head. And then I'll come in here and I'll say while rover doesn't equal null, let's do the following. Let's let rover equal rover.getNext, and let's increment count. And then at the end here, I just return count. And I think we are all done here. Let me see. Again, I like to line up. Okay. And there we go. So that is the first method that I wanted to put back in here. The next one that we talked about is find. And let us come over here. Find. And let's think about, again, how find should work. Here's head. Here's Bill, 23. Here's Mary, 35. Here's Mike, 22. And it's like that. And the basic idea is again, I'm going to have a variable called rover. And I would initialize rover to head. So that means rover is now pointing up here at Bill. And maybe I'm saying something like find Mary. So the idea is I would do a string compare of this with this, and they're not equal. So then what I would do is I would just advance this reference now to point over there. And now I would do a string compare again. They are the same. So at that point, I would just return the value of Rover. If, on the other hand, I was asked to find Karen, the string compare here would be false. So again, I would advance it to here, and I would do a string compare, and it is not the same. So again, I would advance Rover, but now Rover would be set to this. So now Rover would be doing that. So we could almost imagine that we are going to have while Rover doesn't equal null, and we could come in here and we could say something like the following. If rover.getName, I guess we're going to have to write another getter, dot compare to key, and key would be the parameter coming in here. If this is equal to 0, break. Otherwise, what we would want to do is this rover is equal to rover.getNext. And we recognize that if we make it down to this point of the program, one of two things has happened. Either rover is equal to null, or rover is pointing to the particular node that contains the value that we want. So what I want to do here is I want to return rover. And this is basically what the find method should look like. Now we do remember we're going to have to go back to our node class, and we're going to have to write a get name in there. So I'm going to come over here and I'm going to go to node, and notice here we have a set next and a get next, but we don't have a get name. So I'm going to come over here and I'm going to say public string get name, and I will just return name. And we're fine with that. I am going to come over here to linked list, and I am going to say public node find string key. Okay, so first of all, notice that what this thing does here is it returns a reference. Okay, and remember, it will return a reference to the node if it finds a node that has key for name, and it will return null otherwise. So I come over here, and I am going to say, node rover equals head. And then I'm going to come in here, and I'm just going to write that loop that I had before. So I'm going to say while rover doesn't equal null, what am I going to do? Okay, I'm going to say if rover.getName dot compare to key, whoops, I've hit the caps lock key. If, let me see, if that's equal to 0, then what I want to do is break. Otherwise, I want to set rover equal to rover.getNext. And then what I want to do down here is I want to return rover. And let me see, what is the problem now? Again, my fingers are just not behaving the way they should be. There. Now everything is fine. Okay, And finally, the last thing I want to do is delete front. Now remember, the way that we want this to work so if this is Bill, and this is Mary, and this is Mike, and it looks like that, and I do delete front, what I want to do is I actually want to, and I think I'll change colors here, I want to change this to that, okay? The other thing I want to do that's going to be a little bit strange, but you're going to find we're going to be doing this for all of the dynamic data structures that we're going to be studying. When I delete something, I want to return a reference to this. So basically, what's going to happen is if delete works, it should return a reference to the object that was deleted. Okay? And if delete doesn't, if it's unable to delete, it should return the value null. So this isn't going to be so hard. So normally, what I would want to do is I would want to have something like a node, and I'm going to call it return node is equal to head. And then what I want to do is I want to say head is equal to head dot get next. So you can see what I'm doing over here is this is going to be the variable that I'm calling return node. Is going to get this same value here, and then head gets head dot get next. So now head is pointing to this over here, and then what I would want to do is return the return node. Okay, and that seems fine. But I ask the following question. Suppose the list only has one node in it. Well, if I come over here and I say node return node equals head, then return node is indeed pointing to that thing up there, and then head is equal to head dot next. So the list gets updated and it looks like this, and I'm returning this. That seems okay. This is okay. But now, suppose this thing is initially null. So node return node would also get set to null. So return node would also get a null. But then I say head is equal to head dot get next. For an empty list, this is an exception. If the list is empty, this throws an exception. So basically what I need to do with this statement over here is I need to put a guard in. A guard is an if statement. If head doesn't equal null, then we want to go and do this. Okay? But in either case, whether head is equal to null or head doesn't equal null, I wanted this was initialized to head. This would return null. So in that case, we're okay. So if I come back over here and I say public node, not noid, delete front, and then I come over here and I say node return node equals head. Okay, and then according to what I wrote over here, then I need to do this guarded statement, or the statement with an if in it. And I need to come down here and I need to say if head doesn't equal null, then what I want to do is head is equal to head dot get next. And then I need to come down here and I would say return ret node. So now let's come over here and let's just watch everything run. So I'm going to come over here. So you may recall this from the last video. This is just I'm going to be able to add some names. I'm going to come over here and I'm going to say before delete front, and I'll come over here and then I'm going to come over here and I'm going to print it out, and then I'm going to do a my list dot delete front, and then I'm going to say after delete front, and then I'm going to come over here and again list it out. And then I'm going to come over here and I'll say something like node where equals my list dot find bill. And then I'll come over here and I'll say something like if where doesn't equal null, I'll just print it out. It should print out the whole thing. Else okay, so this is a simple test. Let's go ahead and run this. I'm going to run it again. Okay, so I'm going to say enter another name, and I'm going to say yes. And I'm going to come in here and I'm going to say Sue, and I'm going to say Sue is 34. And then I'm going to come in here and I am going to say Mike. Oops, I have to say yes, yes. Mike, 55. Enter another name. I'll say yes. Bill, 21. I'm going to say no. And let me make this window bigger. So you will notice that before delete, it was Bill, Mike, and Sue. After delete, it was Mike and Sue, and it said not found. Okay? So this is not a completely thorough test of it, but I think that we have gotten the things working correctly. So here is using the linked list. Here is the actual linked list. And here is the node class right here. Again, this is in your book, but I'll put this up on Canvas. I want to finish up this discussion here by just saying one more thing that I think is very, very cool. Let me... The way that we have implemented a linked list so far is I want you to recall that the linked list grows with insert front. And the linked list shrinks with delete front. So what you should recognize here is what gets deleted first is the newest thing that's put into the thing, okay? And you should recognize that as a LIFO data structure. Okay, which means that this thing is really a stack. What we've implemented here, this is a dynamic stack. And the thing that's very cool about this as opposed to the static stack that we've done previously is there's really no memory limitation on this thing at all. We don't have to declare up front an array to hold 10 elements or 20 elements and then worry if we wanted to push more than 20 elements on it. This thing can keep growing and growing and growing and then shrinking and shrinking. So this is a dynamic stack, and that's a very, very important point. So give it some thought, and that is the end of this video. Thank you.